All right, so this is a small case study that is meant to show how to integrate a pump model with a model of some system that includes a pipe and a valve, and then simulate that system. So here's a schematic of the system. We have a centrifugal pump, and it's connected to some length of pipe, and then at the end of the pipe we have a valve. So this is a very typical kind of a situation, and we might want to understand here, what is the flow rate that we would get as a function of the valve position, so basically how much we shut the valve, and also the pump speed if we can control the pump speed. So in any situation like this, however simple it might end up being, convergence can become an issue, and so you got to be a little bit careful. So in this case, I'm going to define my input parameters. These are things that are kind of set, and that's going to be things like the fluid. The fluid is an ATF heat transfer fluid. The inlet temperature and pressure, so just room temperature, atmospheric pressure. The size of the centrifugal pump is going to be a 5 centimeter centrifugal pump with a 1.5 centimeter hub, and then the pipe is going to be 1 centimeter in diameter, inner diameter, and 1 meter long. And then the valve itself will have the same inlet area as the pipe. It's going to be a globe valve, but I can adjust the position of the stem in order to change the area at the seat, and then change the restriction of the globe valve. So those are my inputs. They're not going to change. The things that I might want to adjust would be the pump speed and the position of the valve. So this F0 parameter is the ratio of the seat area to the inlet area. So that would start at 1 and go down from there. Actually, I guess it could be greater than 1. But as you close the valve, that's going to go towards 0. And then finally, I need to identify the iteration parameter and how I'm going to eventually adjust the iteration parameter to get convergence. So the mass flow rate through the pump and the pipe and the valve, they're all the same mass flow rate. That mass flow rate is going to be adjusted. That's going to be my iteration parameter, and it'll be closed by assuring that the pressure rise across the pump is equal to the pressure drop through the pipe plus the pressure drop through the valve. So that's the approach I'm going to take, and I start by entering. I'm going to start by loading the component library. So right at the top here, I'll put a $load component library. I'm going to set the units because I'm going to get some properties. So here's a $unit system directive, and then I'll enter my input parameters. And again, these include things like the fluid and the inlet conditions, the size of the centrifugal pump, the size of the pipe. And then I'll enter my operating conditions. So things I vary will be the speed of the pump and the valve position. And then finally, my iteration parameter, initially I'm just going to set it to be some reasonable value, maybe 0.08 kilograms per second. And now I have to go off and simulate each of these components. So I'm going to simulate the centrifugal pump using the component library. So if I go to the component library and go to pumps, you'll see that there is a centrifugal pump model, and that's the one I'm going to choose. And I have to paste it in here. And you can see there's a bunch of things that it requires as inputs. It needs the fluid, which is that fluid string. If it were a solution or like a ethylene glycol mixture, it needs the concentration, but it's not. So we can just put a 0 here. It needs the inlet conditions, inlet temperature and pressure, and the mass flow rate. And then it needs the speed of the pump, the outer diameter of the pump, and the hub diameter. And it's going to give me back the outlet pressure, the outlet temperature, the power that it requires, and the efficiency. And so the pressure rise that it produces is just this outlet pressure minus the inlet pressure. And then I'm going to try to simulate the pipe. So here I'll go to the heat transfer library where there's a large number of internal flow models. So here I want pipe flow. I'm just going to pull the dimensional version down. And I give this the fluid. I'm going to give this the inlet conditions to the pipe, which are the outlet conditions for the pump. It needs the mass flow rate. It needs the pipe size, the diameter and the length, the relative roughness, which we're going to assume is 0, so it's smooth. And it gives me back a number of things here. The only thing that I'm going to keep is delta P pipe. So everything else I will just leave blank. I have to leave commas in the right spots. Delta P pipe, it looks like, is the third output, so it's got to remain the third output, but I don't care about the other ones. All right, and then I need to simulate the valve. So the valve is a globe valve. I'll go here under function information, and I will I think have to go to minor losses and flow measurements. I think that's where we'll find it. And we'll go down to valves, and you can sort of scroll your way through the different valves. This is a globe valve, which is this third one, and we'll paste that in. It requires the roughness, and it requires this position, which is defined as the area at the seat divided by the area at the inlet. So that's what I've pasted here, and it's going to give me back this K value, which is a flow coefficient. So that's not the pressure drop. If I want to turn that into the pressure drop, I have to multiply that by the inlet head, right? So the 1/2 rho v squared at the inlet. So to get that, I'm going to have to calculate the density. So that's what I'm doing here. And the volumetric flow rate is just m dot divided by rho. And then the velocity is the volumetric flow rate divided by the inlet area. So the inlet area is the same as the pipe area. So that's what I'm doing here. And then delta P is just 1/2 rho v squared times K. And I got to be a little careful because this is going to give me pressure drop in pascals, and all of my other pressure drops are in kilopascals according to my unit system up here. So I'm going to convert that to kilopascals. So now I have the pressure rise produced by the pump, and then the pressure drop produced by the pipe and the valve. And the way that I'm going to close up my iteration parameter m dot is by requiring that these pressures match up, right? And whenever you're iterating, what you find is that it's very important that you've defined some balance for your iteration variable and a good guess value. And the way that I can sort of control that easily is right up here at the top. I'm going to put a $var_info m dot, and my lower bound, so lower equals some m dot min, which I'll come back to in a second. Upper is m dot max, and guess is some m dot guess. So let's start with m dot max. The maximum possible flow rate would be the flow rate I would get if the pump was producing no pressure rise. And I can get that from the centrifugal pump model. I'm just going to call it again down here, and I'll give it, the same things: the fluid, the concentration is 0, the inlet condition, temperature and pressure. It's going to give me m dot max. So this argument here, this input argument, is actually what I'm calculating, m dot max, and then the speed and the size of the pump. And then the outlet pressure, when I'm getting the maximum flow rate, is equal to the inlet pressure. So I'll just put P in here. And under these conditions, I don't care about the other outputs, so I'll leave them blank. And if I solve this, it'll tell me the maximum possible flow rate produced by the pump, which will be a really good upper limit to limit my search, my iteration for. So that's what I'm going to use for upper. The guess value, I don't think it matters a lot as long as it's in the range, so I'll just take m dot max and divide it by 2. And then m dot min probably shouldn't be 0, because at 0 you're going to find that with 0 flow the outlet temperature tends to explode to infinity. So some relatively small mass flow rate would be a good thing to put there. So that's what I'll put here. And with those limits and the guess value set, now when I come down here and comment out m dot and instead constrain delta P pump to be equal to delta P pipe plus delta P valve, I'm going to find that it's going to solve with no problem over a fairly wide range of conditions, which is really nice because now I can exercise this model to do all kinds of things with it. So one thing that we could do is make a contour plot that shows the flow that you get as a function of the pump speed on one axis and the valve position on the other. So basically, your two control parameters. And to do that, I'd make a parametric table. I'm going to put 400 runs in this table, so that'll give me 20 pump speeds times 20 different valve positions. And we'll go ahead and we will alter the values. So let's put all the stuff we need inside of here. So we need to put inside of here the volumetric flow rate for sure, the valve position, the speed. Maybe I want the mass flow rate and the pressure rise as well. And then I'm going to adjust the valve position. So I'll hit alter values, and I'm going to go from some very small values, so much less than 1, which basically means I've closed the valve down, so maybe 0.01, all the way up to 1 in 20 increments. And I want to do that over and over again. So apply that pattern every 20 rows, and then I'll do the same thing for the pump speed. I'll go from maybe 5 revs per second to 30 revs per second, and I will actually repeat that pattern every 20 rows. And so I get this sort of grid of pump speed, valve positions over the entire range, and I'm gonna come over here and comment them out and solve the table. And now I can represent these data as a contour plot. So if I want to make a contour plot, I'd hit new plot window, XYZ plot, and I'm going to put one of my independent parameters on the X, the other on the Y, and then my contour variable will be the volumetric flow rate. Probably in liters per minute would be the best way to do that. And I can change the resolution and stuff like that. But in the end, I get this nice contour plot. And it's actually remarkable that the model was able to converge over this wide range of conditions, going from almost all the way closed to the valve to wide open, and then the pump speed all the way down towards 0 to full speed.